For most of us, there is no object more interesting and fascinating than black holes sitting in the dark voids of the cosmos. Black holes have deeply fascinated us for about a century now, and we are still trying to figure out how these things really work. What makes them so unique, fascinating, and terrifying at the same time? To understand what these mysterious objects really are, and what implications do they have for the science of the future, first we have to take a closer look at the past. The past in which the groundwork for understanding these black holes were laid by our great pioneers. The story of black holes starts at a time when a rather seemingly unrelated conflict in physics was developing. By the late 19th century, physicists were struggling to grasp the true nature of light. You see, the study of light worked as a great catalyst to change the very structure of modern physics and to reveal many wonderful insights. Through the study of light, we were able to discover the deeply hidden secrets of the cosmos. At that time, scientists were fixed as to which theory of light was correct. The theory that light is made of particles, or the theory that light is a form of electromagnetic wave. And the most important question was how light would interact with gravity. At that time, it was believed that light travels at an infinite velocity. So, no matter which theory of light is correct, it would still not be affected by gravity, right? But later discoveries showed that light has a finite velocity, and anything with a finite velocity will definitely be affected by gravitational attraction. Now, if light is made out of tiny little particles, then it would make perfect sense that light will be pulled away by gravity. But what if light is a form of electromagnetic wave? How would gravity interact with an electromagnetic wave? And these were the hard-pressing questions back in the early 20th century. We now know that light has a dual nature of particles as well as of waves. But back then, a revolutionary change in thought was needed to clearly understand the interaction of light and gravity. This revolution was brought forth by Albert Einstein's ideas. He completely changed the way we imagined gravity. According to his theory of general relativity, gravity is experienced when an object is trapped inside the curvature of space-time caused by the presence of a massive object. Einstein thought gravity to be nothing more than a curvature in the continuum of space-time. Now, gravity was not a mysterious force which attracts different objects like magnets. An object simply falls in the curve of space-time created by the mass of another object, and we say it is falling due to gravitational attraction. So the puzzle of whether light would be affected by gravity was now solved. Light travels in straight lines in space, and if space is bent, then it followed that the path of light would also be bent, regardless of its composition. And it has been observed in phenomena such as gravitational lensing, so we can now confirm that light is affected by gravity. Now let's explore a different idea proposed in 1783 by a Cambridge professor named John Michell. In a paper, he had suggested the existence of such massive stars whose gravity is so strong that not even light could escape from their surfaces. Although it was purely a hypothetical suggestion, many great thinkers at that time began to formulate new ideas and concepts around it. Slowly, new studies were conducted on this topic of so-called black stars by physicists as well as astronomers. And the great breakthrough came when a young Indian physicist sailed to Cambridge in 1928. His name was Subramanian Chandrasekhar. Chandrasekhar worked extensively on this topic of hypothetical black stars and formulated how a star evolves in its lifetime. Stars are created when a large amount of hydrogen gas begins to gather around itself due to gravity. Gradually, the mass and the size of this gaseous body grows to such an extent that it emits light and heat generated by the fusion of hydrogen atoms within its core. The energy generated by this process counters the gravity acting towards its center and prevents it from collapsing within itself. The more massive the star is, the more energy is needed to counter gravity. That is why the giant stars run out of their fuel much sooner than the smaller sized stars. For a star like our Sun, there is about 5 billion years before it runs out of its fuel. So Chandrasekhar asked, what happens when a star runs out of its fuel or hydrogen to produce sufficient energy? to prevent it from collapsing. He then came up with a startling discovery. He found that if the mass of the star was not sufficient enough or below a critical point, then the gravity would not be so strong as to completely collapse it into a point. This critical mass is known as the Chandrasekhar limit. It is around 1.5 times the mass of the Sun. The mass of the Sun does not exceed this limit. Therefore, after fuel exhaustion, it will not collapse into an infinitely dense point. It will shed off its outer layers and become a white dwarf. At that time, our telescopes were not sophisticated enough to see any white dwarfs. But later observations showed that there are a large number of white dwarfs existing within our own galaxy. So now the question arises, what happens to a star that has a mass beyond the Chandrasekhar limit? Many scientists at that time were against the idea that stars could collapse into a point with infinite density, and they believed it was not possible in reality. Due to peer and academic discouragement, and Chandrasekhar left this line of work and focused on something else. The next breakthrough in this investigation came from a young American scientist, Robert Oppenheimer. Oppenheimer sought to answer what would really happen if a star begins to collapse into infinite density. He explained that slowly the star's light would look redder and fainter because it would be hard for light to escape the hugely curved space-time around the star. And after a certain amount of time, no force within the star would be able to stop its complete collapse into a black hole, from which no light can escape. Light is the fastest thing in the universe, and if light cannot escape, then nothing else would. This black hole has a boundary called its event horizon, where we can see the path of light bending towards the infinite darkness. At that time, there was no way to detect black holes in outer space. Their discovery took decades after these theories had been formulated in paper, and then the real observational data confirmed these theories of our pioneers and showed us a new way to study stars and their evolution. These are the phases through which we have been able to discover the existence of black holes, and still they are mysterious as ever. Our current scientific theories seem to be inadequate to tackle the problem of these mysterious bodies, and therefore if we are to solve the black hole problem, then we need a new revolution in science, maybe a theory of everything. I thank you for watching this video till the end. If you learned something from it, then don't forget to like and subscribe to the channel, because more and more informative videos are coming.